will say it like that, that curve is concave up. So you can kind of think about it as, you know, it would hold water if it's concave up. Okay. And if it's turned the other way, that means that it's concave down. So I want you to think about what happens to the first derivative before we talk about this definition you see below. Remember that the first derivative gives you the slopes of the tangent lines, right? So I hope that you can see, I'm trying to sketch little tangent lines on this curve when it's concave up. Notice what happens to the slopes of those lines. So when I did this first one over here, notice the slope of that line. It's negative, it's kind of steep. Notice here, the slope is still negative, but it's not as steep. Okay, when it gets to here, we can see we would have a horizontal tangent line at 0. Here, the slope is positive. Here, the slope is positive and it's steeper. If it's steeper, that means it's a bigger value, right? So notice that our first derivative there, those slopes are getting larger and larger and larger. So the first derivative is increasing. The value of the slopes of those lines is increasing, right? And same thing here, if you think about what happens to the first derivative, so draw, you know, some little tangent lines on there and think about the slopes. Do you see the slopes there of those tangent lines are getting smaller and smaller and smaller? Which means that the first derivative there is decreasing. So if I want to find out where the first derivative is increasing or decreasing, I would have to take the derivative of that function. And we know that when we take the derivative of the first derivative, we get the second derivative. So whenever the first derivative is increasing, like I'm showing you here, notice that our function is concave up. And if that first derivative is increasing, that means its derivative is positive. So, and this is probably on the next slide, but I'm going to go ahead and write it here. So if the first derivative is increasing, that means that the second derivative is positive. So whenever the second derivative is positive, that's where our function is concave up. And where the first derivative is decreasing, so that means that the second derivative is negative, that's where our function is concave down. So any questions or comments about that before we go on? Okay, if you have a curve that changes from concave up to concave down, so in this one, it looks to me like that would happen about right here. So notice to the left over here, that function is concave down, but then at some point it becomes concave up. That point where the concavity changes is called an inflection point. So notice that an inflection point is a point where the concavity changes. And we are going to learn how to find those points. And this is what I just jotted on that slide up above, only it's written neater here. Okay, whenever you're testing for concavity, remember that the second derivative tells you about the concavity of a function. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. If the second derivative changes sign, so it goes from positive to negative or vice versa, that's where you will have an inflection point. So just to summarize, because we're going to have lots of functions floating around, when we have y equals f of x, the original function, okay, so I'm going to say that I'm going to call this the original function. The original function will always give us the y coordinate of a point, right? The first derivative is where we get where a function is increasing and decreasing, and where we get critical points. Critical points always come from the first derivative. The second derivative tells us about the concavity of the function. And we can use the second derivative to find inflection points. So just to have them all together, that's the information we get from those different functions. So any questions or comments about that before we do a problem where we decide where the function is concave up and concave down? It's kind of easier to keep straight, you know, like of course the second derivative tells you about concavity when we're really focusing on that. But when you start working a problem and you have all those functions written down, lots of times it's easy to get confused and start plugging things into the wrong function. So try to stay really organized and just label them so you can tell yourself what you need to find from those functions. Okay, so here's an example. So our question said this time says determine the intervals where the function is concave up or concave down, and then identify any inflection points. So we may or may not have any, we're going to decide. Okay, but if the function or the question asks you about the concavity of the function, that's how I know I need to find the second derivative. But we know that we have to find the first derivative first. So let's start there. So when I find the first derivative, we're going to use the product rule. So the first times the derivative of x minus 3, which is 1, plus the second times the derivative of the first. So I used the product rule. We want to make that look as nice as we can before we take the derivative again. So I'm going to factor an e to the x out of that. If I factor out an e to the x, then, and of course, there are different ways you could think about it. So if you would rather, you could have distributed that e to the x and then combined like terms. That would have been fine too. So it may be written differently, but even if you thought about it a different way, it should be equivalent to what I have there. So any questions about the first derivative? All right, so now we need to find the second derivative. And that's why we want to simplify that first derivative as much as we can, right? But to make it easier to take the second derivative, because then I'm going to do the same thing again. I'm going to use the product rule. First times the derivative of the second, but that's just 1, plus the second times the derivative of the first. And I'm going to factor out that e to the x again. Okay, and by the way, today we are learning how to find all these different pieces of information. What we are going to do tomorrow is find everything and learn how to use it to actually sketch the graph of the function. And this one will be kind of an interesting graph for us to look at. So make sure that you have your notes from today handy, because we will use this function as one of our examples tomorrow to save us a little bit of time since we've already found some of the pieces. All right, but any questions at all about the derivatives before we go on? All right, so the question really asked about the concavity. And to decide where this function is concave up or concave down, we need to find out where the second derivative is positive or negative. And the second derivative can change sign whenever it's equal to 0 or where it's undefined. That's where any function can change sign, go from positive to negative. So we are going to find the places where the second derivative is either 0 or undefined. Well, first of all, I can see that there are no places where it's not defined, right? E to the x is defined everywhere. X minus 1 is defined everywhere. So I'm not going to get any solutions out of that part. So now I'm setting this function equal to 0. We know e to the x can't be equal to 0. E to the x is always positive. So it looks like the only place that this function could possibly change sign is at x equals 1. And as always, please stop me if you have a question. I don't mind at all if you interrupt me. This x equals 1, where your derivative is 0 or undefined, is a possible inflection point. But at this point, I do not know if it's actually an inflection point or not, because it is possible for the second derivative to be 0 and not have an inflection point there. I'll show you an example of that in just a minute. You don't know if it's an inflection point unless you know the concavity changes. That's the definition of an inflection point. It's a point where the concavity changes. So to decide, what we're going to do now is mark that possible inflection point on the number line. And remember, we're talking about the second derivative here. Make sure you don't call that point a critical point. It is not a critical point. A critical point is a place where the first derivative is 0 or undefined. So we'll keep working on the terminology until that kind of gets in your brain really good. All right, but we're going to do something that looks very similar to what we did before. We made a sign chart. We want to know where the second derivative is positive or negative. So I pick a point to the left of 1. I'm just going to pick 0. And I want to know about concavity. So I need to plug that into the second derivative. So notice I plugged it in right here. This was my second derivative. And when I do that, will my answer be positive or negative? Good. We're going to get a negative answer. 1 times negative 1 is negative. And again, I'm a very visual person, so I like to think about it. Second derivative tells me concavity. If it's negative, I know it's concave down. So I'm drawing something there that looks concave down to remind me. So I test the other interval. I pick something bigger than 1, so I'm just going to pick 2. If we plug in 2, we would get e squared times 2 minus 1. So of course that's positive, which means it's concave up. So the question says, determine the intervals where it's concave up and concave down. So make sure you don't stop there. I know you're not tempted to stop there when you write the answer in MyMathLab because it prompts you to actually write the answer. But if this is a grade scope problem, make sure you actually answer the question. Okay. So now I want to give the intervals where it's concave up. So I look at my chart and I notice that it starts being concave up at 1 and goes to infinity because the domain, I should have said this earlier. I kind of hinted at it, but I didn't actually write it down. Notice the domain of this function is negative infinity to infinity. And this function is concave down everywhere to the left of 1. And so then the question becomes, do we have an inflection point? So can you tell me, do we have an inflection point at x equals 1 this time? Yes, the inflection point occurs at x equals 1. And sometimes it will just ask you for the x coordinate of the inflection point. But if it actually asks you for the inflection point, make sure you write it as a point. How do we get the y coordinate? Yeah, plug it into the original function. Every time you need the y coordinate of a point, you always plug it into the original function. So notice I go back to the top to the original function. I'm plugging in 1 for x, so 1 minus 3 is negative 2. So I would get negative 2 times e to the first. Don't change that to a decimal. Unless the problem actually says round or approximate, you would never change it to a decimal. Okay, so this was the answer to part B. Sorry, I didn't mean to make that go away. This was the answer to part B. This was the answer to part A. Any questions at all about that problem before we look at another one? Oh, how did I get minus 2e? I plugged it into the original function. Notice that x is 1. So I found f of 1, e to the first times 1 minus 3. Every time we want a y coordinate, we would plug it into the original function. Yeah, and that's what I meant earlier. When you have all those functions floating around, it's easy to accidentally plug it into the wrong place. So just kind of slow down for a minute and make sure that you're using the right function. Any other questions about that one? We're going to try another one. Okay, so same directions for this guy, only we can see this one is not as nice of a function. So before I do anything else, I think that we actually used this function for something last time, but let's write the domain of the original function. What is the domain of that function? Because we don't want to give any values for critical points or inflection points that are not even really points. It has to be defined. Where is that function defined? Yeah, for all x's greater than 0, right? Because we're taking the natural log of x. And so we know that x has to be greater than 0. So let's keep that in mind. All right, but the question asked about concavity and inflection points. Okay, that was the question. I scrolled up so you can't see it. Same directions as before. So that means that we need to find the second derivative. So of course, we'll start by finding the first derivative. So I have the first times the derivative of the second, but we know the derivative of the natural log of x is 1 over x, plus the second times the derivative of x to the 1/2. So that would be 1/2 x to the minus 1/2. And I'm definitely going to clean that up before I take a second derivative. But please let me know if you have a question about how we got that before we go on. So I'm getting a common denominator. I want that first derivative to look as nice as I can make it look before I take a second derivative. Okay, if the problem asked me to find where the function is increasing or decreasing, I would stop and use the first derivative. But we need to find concavity, so I'm going to keep going. So what rule should I use to find the second derivative? Yeah, I'm going to use the quotient rule. Good. You could rewrite it and use the product rule if you want, but it's going to be about the same amount of work either way, so I'm just going to use the quotient rule. So I have the bottom times the derivative of the top. Help me out. What's the derivative of the numerator? Good. The derivative of 2 is 0. Exactly. The derivative of natural log of x is 1 over x. That's great. Minus the top times the derivative of the bottom. The derivative of x to the 1/2 is 1/2 x to the minus 1/2, all over the bottom squared. And that looks like a horrible mess, so we are definitely going to simplify it. I'm going to rewrite it first so I don't have any negative exponents. I have 2 square root of x over x. So that's going to be 2 over the square root of x. Notice 2 times 1/2 is 1. So I'm going to have minus 2 plus the natural log of x over the square root of x. So I'm just trying to clean it up a little bit. Never leave complex fractions, so I'm going to multiply the top and the bottom here. X. So I have 2 over the square root of x times the square root of x. So the square root of x's are going to cancel out. That's nice. Minus, same thing here when we multiply. Whoops. This would be 4x times the square root of x. 2 minus 2 is 0, so it looks like I have minus the natural x on top, 4x square root of x on the bottom. All right, so any questions about that derivative before we go on? Because that's what's really different now about when we find those derivatives. Because back in chapter 3, we found them and we didn't worry about simplifying them too much because we were just concentrating on just finding the derivative. But if you're going to use that derivative to do something else, you're going to have to do some algebra stuff to simplify them. And it's been a long time probably since you have done some of that algebra stuff, so I don't mind at all if you ask about it. As you practice doing your homework problems, it'll come back to you. That's probably going to be the hardest part of some of these problems, is just getting the derivative simplified, because now we have that second derivative. Can you help me out? Do you remember what we do next? Once we have the second derivative, we're trying to decide where it's concave up or concave down. So what's the next step? I think you have the right idea there, Jamie. Good. We're going to find where the second derivative is 0 or does not exist. But remember, those are not critical points because critical points always come from the first derivative. If we found out where the first derivative is 0 or undefined, those are critical points. But you had the right idea, I know. Right, it's just a terminology thing, right? So when we set the second derivative equal to 0, or where it's undefined, what we're finding there are the possible inflection points. Okay, but remember that we won't know if they're actually inflection points until we check to see if the concavity changes. All right, but if we set that equal to 0, it will be 0 whenever the top is 0. It will be undefined whenever the denominator is 0. Right? Or where the top is undefined. That's actually going to happen at the same place this time. I'm going to go ahead and talk about that one first. We know this is 0 when x equals 0, and notice that would also make the top undefined. In this one, could x equal 0 possibly be an inflection point for this problem? Yeah, do you see if you go back up and look, it's not in the domain. Right? If it's not in the domain, that means it's not going to be an inflection point, because a point means that it's a point on the curve or on the graph. But that's still an important point. So that's kind of what I was telling you earlier. When you draw your number line, which I know we still need to do that first part, we're going to do that. Even if that's, already that's not an inflection point, or if we were using the first derivative, we would know that's not a critical point. You still want to make sure you have that point on your graph, because it's still an important point, but I know that it's not an inflection point. And in fact, since I went up and pointed at the domain, let's go ahead and talk about that. The domain of this function is from 0 to infinity, which means we don't worry about any of this stuff over here, right? That's not in the domain of f. So no matter what happens, I'm not going to be plugging in any numbers over there. Okay, but back to the place where the second derivative is 0. I have the natural log of x equals 0. Where is the natural log of x equal to 0? If you need to, put that step back in. Remember, natural log is an abbreviation to mean log base e. Change that to an exponent. E to the 0 equals x. I do that so many times in my algebra class that I know my students just want to pull their hair out. Okay, because it's hard to see, like, whenever you're going to run into those functions, but we are going to run into them a lot in calculus class. So the solution there is e to the first. So that means I might have an inflection point at e. We're going to find out. But that's a place where my derivative could change sign. So now I'm going to test my intervals. I have to pick a number between 0 and e. Well, we know that e is about 2.718. So just pick something nice. So I'm just going to plug in 1. When I plug in 1, what should I plug it into? Right here, I made a mistake. So right there, I wrote it correctly over here. And I realized I made a mistake when I started to plug it in, right? E to the 0 is 1, not E. Sorry about that. I realized that when I started to plug it in, I'm like, I'm going to get 0. So I know something's wrong. Make sure you fix that on your paper, and let me know if you have a question about that before we go on. E to the 0 is 1. I wrote e to the 0 equals e to the first for some reason. Okay, so this is our possible inflection point. So I can't pick 1, right? I've got to pick something between 0 and 1, so maybe 1/2. If we were going to find the y coordinate for x equals 1/2, we would plug it into the original function. But we are trying to determine the concavity. If we are trying to determine the concavity, which is what we're trying to do when we make this sign chart, what function do we plug it in to determine if it's concave up or concave down? Yeah, the second derivative. This sign chart here is for the second derivative. So this is where I'm plugging it in. And you can use your calculator to help you with the arithmetic if you want, but I hope you know the natural log of 1/2 is 0. If I just make a little sketch of the natural log function, this is y equals natural log of x. Anything between 0 and 1, I get a negative value there. But notice I have a minus in front of it. So I have minus something negative, so I know the numerator is positive. 1/2 times the square root of 1/2 is positive. So my function would be concave up there. I pick something to the right of 1, like 3. Remember, I'm plugging it into the second derivative, so I would have minus the natural log of 3, but the natural log of 3 is positive, so that's negative. If I plug 3 into the denominator, that's a positive answer. So a negative over a positive, so it's going to be concave down there. Any questions at all about that chart before we write down the answer? Okay, so then just look at your graph. It's concave up from where to where? From 0 to 1. So make sure you don't say negative infinity to 1 because it's not defined to the left of 0. So you're exactly right, from 0 to 1. It's concave down from 1 to infinity. And since the concavity does change there, that means we actually do have an inflection point. The x coordinate of the inflection point is 1. And anytime we want a y coordinate, we go back to the original function. So I'm going back to the top. So to my original function up here, f of x equals the square root of x natural log of x. If I plug in 1, I would have 1 times 0. The natural log of 1 is 0. So that would be my inflection point. So any questions about that problem before we go on? And again, tomorrow we're going to be graphing, and it takes a long time to do those problems because we have to find all this information and then sketch a graph. So, try to make sure that if you need to kind of make your notes a little neater or something after class, kind of get it all together as organized as you can, because we are going to use these as some examples in class tomorrow. But we've got part of the work done, so that'll save us a little trouble. So now we're going to start looking at some graphs. And we've done a little bit of this before, but now we're going to do lots more of it. And these problems are to make sure that you understand what the derivatives tell you about a function. So notice in this picture that we are given the graph of the first derivative. That's the one that you see in pink or red there. And the graph of the second derivative. So that's the one in the blue. And we are supposed to sketch the graph of a possible function of f. That means that our graph will have the correct shape, right? But we may not be able to tell exactly what the y values are. All right, but we just want to make sure that it has the right shape. Okay, so let's start by thinking about what this derivative tells us. And I'm actually going to do this by drawing a little sign chart underneath. And I am looking at the first derivative. I'm going to mark what we have learned about the first derivative on my sign chart. I can see by looking at this graph, do you see that my first derivative is 0 right here? I'm trying to line this up. So right here, that's a critical point. I'm going to call it C1 because that's the first critical point. But everywhere that first derivative is 0, do you see what I'm doing? So let me know if not. I'm going to I'm marking those critical numbers on a number line. And notice that to the left of this first point, so I'm looking right over here to the left, is the first derivative positive or negative there? So to the left of that point that I called C1, is the first derivative positive or negative? Yeah, because we can see that if we look at the graph is below the x-axis. That means the first derivative there is negative. What does that tell us about our original function? What does that tell us about the original function? If the first derivative is negative. And it's fine if you need to look back at your notes, that's fine. If the first derivative is negative, what do we know about our function? Good. If the first derivative is negative, that means the original function is decreasing. So do you see I'm drawing that little arrow like we did earlier? That's what I know. And between C1 and C2, so you see right there, between C1 and C2, do you see our first derivative is above the axis? That means the first derivative is positive. And if the first derivative is positive, that means the original function is increasing. So these little arrows I'm drawing right here represent the original function. First derivative was negative. Now the first derivative was positive. Here, notice the first derivative is below the x-axis. That means the first derivative is negative, which means the original function is decreasing. Here, the derivative is positive, so the original function is increasing. And I need you to let me know if you are not sure what we're saying there. So let me know, is that okay? Or do you have a question about that? Either way, let me know. What about everyone else? Thank you. I appreciate you letting me know that you're with me. And we could sketch we could sketch a curve from that, but since we have the second derivative, we can find out even more information. I'll draw it at the top so it's not messy. So now I am looking at the second derivative now. So notice where the second derivative is 0. Do you see how I'm marking those points? I'm going to call that P1. Okay, that's a possible inflection point. And right here, wherever the second derivative is 0, that's where we might have an inflection point. And we're going to be able to tell. So I'm worried about now where the second derivative is positive or negative. So I'm looking at this blue curve. So notice to the left of this point, our second derivative is positive. So that means our curve is concave up. I'm talking about the original function now. The original function is concave up there. In this middle part, where the second derivative is negative, it should be concave down. And when the second derivative is positive, it's going to be concave up. So that means that the concavity changes at these points. So that's actually, both of them are actually inflection points. And now I'm going to sketch a possible curve for F. Okay. And I do not know the y coordinates, but I know what shape it has. I can tell the original function, I can tell, should be decreasing, right? But concave up, decreasing but concave up. So what would that look like? Well, it would look something like this. It's decreasing, do you see, but I made it concave up. When it gets to right here to C1, that should be a minimum. Do you see that should look like a minimum point? And then it's going to be increasing, but right there, I have an inflection point. So the concavity changes. It's going to quit being concave up, but it's still increasing. So do you see how I'm making it turn? That shouldn't, if I leave my pen down, it makes a little line there. It turns, okay, but it's still increasing until I get to C2. Did I cross it? I was trying to talk. I'm going to have to back up just a little bit because at C2, I should have a maximum. Right here, I'm trying to make that look like a maximum. And then notice it's decreasing, it's concave down until it gets to that inflection point, right? And then it starts being concave up, but it's still decreasing until it gets to here. So this is one possible graph of F. I really didn't know that it was above the x-axis, right? That's why it says a possible graph and all of the answers are not unique, because maybe I should have started that down here somewhere. I didn't know that part. I just know the basic shape that the graph has. But any questions at all about how we thought about it to sketch a graph of the original function? Those take some practice. All right, so let's try another one where we're just thinking about, okay, what happens to our function. Really pay attention to the directions. Notice here it says the graph of f prime is given. So this graph is the graph of the derivative, not the original function. So you've got to really watch out for that. Okay. So if this is the graph of the derivative, so part A, ask, where is this function increasing? Can anyone help me out? If this is the graph of the derivative, can you tell me where the original function is increasing? And if you're not sure where the intervals are where it's increasing, that's fair because you're just kind of really digging into these today. Remember that we are looking for the places where the first derivative is positive, right? A function is going to be increasing whenever the first derivative is positive. So if I have this graph of the first derivative, I'm looking for the places where this function is above the x-axis. So do you see where it's above the x-axis? Yeah. It is true. I see that you have a -1 there. It's true. But do you see it actually starts being above the x-axis at -2? So it's above the x-axis and all the way from -2 to 0. And then from 0 to 2. Okay, so there was some hesitation there. So I want everyone to look. Does everyone see why I picked out those intervals? The original function is increasing whenever the first derivative is positive. The original function is decreasing whenever the first derivative is negative. All right, so now that you see how to think about it, in this one, can you tell me where this original function is decreasing? What about everyone else? What do you think? Where is this function decreasing? And by this function, I mean the original function. Yeah, that's where it's below the x-axis. Very good. Between -3 and -2. Okay, so let's see if we can do part B. Part B says find the critical points of f. So what am I looking for when I find the critical points? How do we get critical points? So don't worry about telling me where that happens on this graph yet. In general, how do we get critical points? Good. When the first derivative is either 0 or undefined. Good. So we are looking at only on this interval between -3 to 2. Notice that our first derivative is 0 at x equals -2, and the first derivative is 0 at x equals 0. So those 2 points are critical points. Notice that this function is defined at -1. We can see something interesting happens there, but notice our first derivative is defined there, so that we do not have a critical point at -1, because this is the graph of the first derivative, not the original function. Then it asks, which critical points correspond to a local maximum, local minimum, or neither? So we have just enough time to do this part. So let's look at x equals -2 first. Notice at x equals -2, notice what happens. The first derivative goes from negative to positive. If you're making this sign chart, look, the first derivative is 0 right here at -2 and at 0. And we can see that the first derivative is negative to the left of -2. So the original function is decreasing. That's what we set up here. Between -2 and 0, notice that the first derivative is positive. And from 0 to 2, we're only looking between 0 and 2. It's positive. So can you tell me what happens at x equals -2? Is it a relative max, min, or neither? So if we look at our sign chart, notice at -2, our curve would be going down, and then it goes back up. So that means we would have a local minimum. Good. But notice at 0, so do you see it's going up? And then do you see it's still going up? So that means there would be a flat spot in the graph. So I've kind of sketched a little curve there that might look something like our original function. Okay, but notice that it just keeps increasing. That's what it looks like whenever you have a critical point that's neither a max nor a min. All right, so it's a place where you have a horizontal tangent line because the derivative is 0, but it's not a maximum or a minimum point. Yes, Daniel, a relative minimum and a local minimum mean the same thing. Yes, that's a great question. And I've been trying to kind of use them interchangeably because it really depends on your teacher or your application or your textbook when you go on from here, which way they word it. Okay, so we don't have time to do the rest of those parts together, but I encourage you, go ahead and finish that one. And then if you have a question about it, you can ask tomorrow. And I also really encourage you to go ahead and do that last example that's in your notes for today. Well, I think I had these notes for 4.3 and 4.4 all together in one document, but you should be able to go ahead and do this one. And then if you have questions about those, bring them to class with you tomorrow. But I want you to try them first to see if you can finish them. So we will stop there. If anyone has a question about anything that we have done, I am not in a hurry, but I know that some of you need to go because you have other obligations. So feel free to sign off. Have a great day. But I'm going to hang out here. And if you have extra questions, feel free to stay. You're welcome. You guys have a great day. I will see you tomorrow.
I have a question.
Sure, Bryce, go ahead.
Okay, so I was looking over my quiz